At this time, I would like to welcome Dr. Jane Hill, who's going to be talking to us this morning about infectious disease diagnostics of the future.
Right, thank you everyone. Can you hear me in the back? Yep, great. So thank you for coming this morning. As mentioned, my name is Jane Hill. I'm an associate professor in the Thayer School, and my group focuses on determining the biomarkers for infectious diseases. So if you look at the top 10 causes of death in the United States, you'll notice a couple of them highlighted up there, and those are associated with respiratory tract infections, some bacterial infections in the first group, and then influenzas and pneumonias in the second. If you extend further into the developing world, then you see a lot of kids that die every single year from pneumonias. In addition, and that's probably the highest cause of death in addition to gastrointestinal or diarrheal diseases. And then in terms of the top disease in the world that kills people that's caused by an infection, that would be tuberculosis, and that kills about 1.6 million people each year, adults and kids. And that's just deaths. We all know that sometimes we don't die from an infection, we just have some morbidity. Maybe we're laid up in bed for a few days, maybe we develop something that's quite chronic. So respiratory tract infections, which is what my group focuses on, is interested in preventing those deaths and reducing morbidity as well. So we focus on the lung, and we've primarily focused at this point on bacterial infections of the lung. So those of you who've had an infection of the lung, can you raise your hand? Probably had a cough or cold somewhere. It should be everybody, really. At some point in your life, that should be 100%. So if you had to have that infection diagnosed, does anybody know how that happens? You can raise your hand or yell it out if you'd like. Yes, please. Oh, the physician. No, we're not going to have the physician. Someone who's not a physician. Yes, sir.
Symptoms. Your body's response, and they guess what's really wrong.
Yeah, exactly. I think guess is kind of the optimal word there. So sometimes you'll have a fever, you won't feel so well, and you'll think perhaps I have something, a cough. If you really wanted to figure out what you have, then you typically have to produce a sample. This goes for pretty much any medical diagnostic, unless it's imaging. And that sample in the case of lung infections is usually phlegm that's coughed up. And when it's coughed up, that's called sputum. Sorry to discuss this at this hour of the morning. However, one coughs up a sample of sputum, and then that sputum is grown on plates, these petri dishes with a media that looks a little bit like Jell-O. And then after you've isolated the organism in that way, then you're typically asking questions of that organism, such as what is its antibiotic susceptibility, which can look something like that. So how long does that take? Well, if you've ever accidentally left something, I presume this hasn't happened to most of us for a long time, to grow, like this poor sandwich, then you'll know that growing a microorganism can take some time, sometimes faster than you'd like if you leave it out in a warm car. Clinical microbiology labs in hospitals, for example, have this down to a T. And yet, it still takes days and sometimes weeks to diagnose a particular infection. And if you want even more information, such as the antibiotic susceptibility of that organism, then it can take even longer. So if we take some of my favorites, such as methicillin-resistant Staph aureus, MRSA, then it can take 2 days in a good system, but up to 4 days to really figure out if it really is methicillin-resistant Staph aureus. Another important pathogen, such as Pseudomonas Aeruginosa, particularly important for patients with COPD or cystic fibrosis, again, 2 to 4 days. Now, if you look at the cause of the greatest number of deaths in the world, tuberculosis, it's weeks. It is a slow-growing organism, and in order to culture it, it just simply takes time. Now, tuberculosis. Does anybody know how it's transmitted? Any guesses, Mike? Yes, it's a bit of a cough. And then these aerosols are very small, so they remain suspended in the air for some time. So a patient who may have tuberculosis, and in some countries it's endemic, so you can assume that perhaps the cough and particular symptoms are indicative of that infection, can go from 3 to 5 weeks just coughing around in their homes and in their workplaces, if they're able to work, spreading the tuberculosis. Right? It's completely inadequate. 2 to 4 days is completely inadequate, let alone 3 to 5 weeks. And that's simply because we're using the technology that's associated with the late 1800s. This is Louis Pasteur, who's an amazing microbiologist, amongst other things, in the late 1800s, and he's the one who figured out how to isolate bacteria and so on and so forth. So the same type of technology is being employed today, for the most part, for the diagnosis of these infections. I think if Dr. Pasteur were around today, he would say we can do better. And I agree with that, and others agree with that. So you might think about DNA or nucleic acid-based technologies. And those are pretty amazing. There are a number of issues associated with them, and I'll touch upon one of those in a moment. But you typically still have to isolate the organism as a first step before you can do the DNA extraction and the determination of that causative agent. And that first step can take 16 hours, 24 hours, 48 hours, which in some cases is just too long for patients. In addition to that, a lot of people can't cough something up. So most children are unable to produce a sputum sample. So unfortunately, the children, regardless of how wonderful your DNA-based technology is, would not be served by that. So the ideal diagnostic for infectious diseases, in my opinion, is non-invasive. It's really quick. You get some idea of the phenotype of that organism. So maybe it's antibiotic resistance profile, perhaps it's sliminess, which can impact clinical decisions, and perhaps the diagnostic can even give you prognostic information. And so in my group, we primarily focus on these respiratory tract infections, and we use the small molecules in breath in order to identify the causative agent of infection. So there are molecules amongst the thousands of molecules that are produced in breath that we think are able to reflect what's going on in the lung. So if you consider what a bug is doing in the lung, you may or may not have done this, but we're going to take a moment now and think about it. It's actually living in that lung environment. It's at war with the body, of course, but it's living in that environment. It's eating the things that are in that environment. It's eating you. And it's producing very particular metabolites that are associated with that bacterium. So a staphylococcus will produce a certain type of metabolites, some of which will be in common with Haemophilus or Legionella, but some will be quite particular, quite peculiar to that organism. In addition, the body is mounting first a general response to that bacterium and then a very highly specific response to that bacterium when it's creating antibodies, for example. So there's this dual pieces of information, I should say, that come from the host as well as the bacterium, and some of that comes out in the breath as small molecular metabolites. So this is our hypothesis, my group's hypothesis in pictures. We basically say that if there is this particular bacterium that's present in the lung, that there will be a profile of small molecules on the breath of that patient that are indicative of that bacterium, and so on for each individual bacterium. So we've done a bunch of work in animal models just to prove that this concept is appropriate. And I'm going to show you a subset of those now. So many of you may have your favorite bacterium listed here. These are some of the top bacteria that cause respiratory tract infections in the West. So Haemophilus, Klebsiella, Legionella, Moraxella, Pseudomonas, Staphylococcus, and Streptococcus. And we have measured the breath of mice. Not quite like that, but a little bit like that. They're not as compliant as you might think, particularly when you're making them do things they wouldn't necessarily like to do normally. But we do collect the breath of these mice, and then we run them through some pretty cool mass spectrometry instruments, some of which we redesign the front end of, and some we use off the shelf. And we come up with these breath prints. So what you're looking at are the small molecule breath profiles. This is sort of the molecular weight of the molecules. This is the relative intensity of the signal from the instrument. And what you'll notice, of course, is that there are some peaks, if you will, that are in common with all of these mice, which makes sense. They're the same age, the same type of mouse genetically. They're eating the same diet. But down here in the bushes, which is a little bit difficult to see at this resolution, there are molecules that are quite particular for the type of infection that's taking place in their lungs. For those of you who are interested in the statistical analysis of this data, this is one version of how we look at the data. This is a principal components analysis. And basically what this is showing in 3 dimensions is that mice that have the same infection cluster together in terms of their breath profile, and that's different than mice with infections of a different nature. So we're able to diagnose infection etiology. This was after 24 hours of infection. We proved the infection in a number of different ways by looking at lung lavages and counting the numbers of bacteria present at the end. So we know they were infected. We know they were producing different breath prints. But we wanted to know if a patient walked into a hospital, in this case a mouse murine patient walked into our lab, whether if it had an infection that was 1 day old versus 2, 3, 4, or 5 days old, whether we'd still be able to see a signature that indicated that it had a particular infection. So we did that study using 2 of our favorites organisms, Pseudomonas aeruginosa and Staph aureus, which are arguably the top 2 gram-negative and gram-positive bacterial causative agents of infection in the West. And over 5 days, we were certainly able to see, this is a cluster of mice from day 1 through 5, that had breath prints that indicated that they had either Pseudomonas or Staphylococcus, regardless of the time point of infection, and which were different than mice that had no infection at all. So regardless of the time, at least up to 5 days, and in a mouse, we can tell the difference between infections or the same infection over time. So what about this question, particularly important when we consider things like Ebola, which is fortunately or unfortunately, I guess fortunately for Joe, unfortunate for me, that it's not a respiratory pathogen, but nonetheless, it would be good to know, right, if you've just been exposed versus if you have an infection to a particular agent. And so this is a subset of studies that we've done. This is just another statistical analysis tool where we've looked at Pseudomonas aeruginosa active infections compared to a saline control, so mice that were just given saline in their lungs, compared to dead bacteria. And so we were able to distinguish over a 5-day period whether there was an active infection or whether you've just been exposed to the bacterial agent or had no infection at all. And in addition to that, when we look more closely at these dead bacteria, we found that the host response really was quite specific in that exposure space. So we could distinguish between Staph aureus exposure and Pseudomonas aeruginosa exposure just by looking at the breath print, whether it's 6 hours, 12 hours, 24 hours, or up to 5 days from that exposure. So imagine you've been in some war zone, you may have been exposed to something. You want to know, A, if you've been exposed versus infected, and B, what that agent was. So we've asked more nuanced questions than that. We wanted to know if we could distinguish between antibiotic susceptibility profiles just by looking at the molecules on the breath. And so in one set of studies, we've looked at the difference between sensitive, methicillin-sensitive Staph aureus and methicillin-resistant Staph aureus, MRSA, the one we've heard of. And MRSA is a huge deal. If you have a staph infection, you probably are going to get a MRSA infection, and 40% of us will not make it through that infection unless we're treated early and with some last resort antibiotics, depending. So in our case, we wanted to ask a really nuanced question. So we looked at strains of Staph aureus that only differed in the presence of the few genes that cause antibiotic resistance. So everything else about them was exactly the same. So we gave these mice, a set of mice, these 2 different organisms, only differing ever so slightly. And these are the profiles that we saw. So as you would expect, same mice are infected with essentially the same bacterium. You're going to see a lot of the molecules that look identical. However, amongst those bushes, even just in one dimension in a principal components analysis, like clusters together. So the methicillin-sensitive mice clustered and the methicillin-resistant clustered separately. This was without any antibiotic being given to the mice. Indeed, we found that there were unique molecules present in each category, as well as, of course, molecules that were shared, because they are exactly the same organism with some minor exceptions. And then when we look at those molecules that are shared, we're able to see fold differences depending on the interaction between those genes that confer resistance, we suppose, and the rest of the genome between the methicillin-sensitive and resistant. So these are fold differences that were greater in methicillin-resistant staph, MRSA, and these were differences in those that were sensitive. And then a whole lot of statistics superimposed on that to be sure that we're seeing what we think we're seeing, and be confident about that. So we love what we do, and we like to do it all over because people get sick all over the world, and because this is an issue that's not only a problem for those of us in the West, but also the developing world, as I mentioned. So we primarily do our work here in this region and also in South Africa. In this region, we focus on ambulatory patients primarily, as well as those who have ventilator-associated pneumonia, and we're using the breath of those patients to build up a database of biomarkers that are associated with those particular infections that are the heavy hitters, so Haemophilus, Streptococcus, Staphylococcus, Pseudomonas, etc. In South Africa, of course, maybe not of course, that's a heavy area for tuberculosis, especially with a HIV co-infection. And indeed, the technologies that have been rolled out in South Africa and other places, if you're familiar with GeneXpert, for example, a nucleic acid or DNA-based test, that test is pretty good. You'd still need to be able to produce a sputum sample, so if you're a child, that's not great. But if you have an HIV co-infection, then that test is simply not as good as it is if you don't have HIV. So there's a massive number of people for whom even a DNA amplification test is inadequate. With our other partners in the US and in Europe and other places, we're primarily focusing there on antibiotic resistance. So there's a massive problem with rising resistant rates in most parts of the world, and we're focused on some of those heavy hitters in that area as well. And with that, I shall take questions. There's a lot of them. We'll start here, Mike. Yeah.
So have you looked at patients that have been treated, that are infected, that have been treated, and see if you can figure out whether they can recover or not?
So the question was, I think, have we looked at patients through treatment? And can we see differences if they've gone back to baseline? And so we're just doing some of those studies at the moment in a range of patients. We have an upcoming study in South Africa looking at patients through time, through basically an 18-month time period, because it takes a long time, right, for that treatment to fully work its way through. And then we'll have some patients here that we've just started to work with, some of them in the chronic infection space in terms of cystic fibrosis, and others that just have kind of walking pneumonias. So yes, we don't have the data in yet. Right. Yeah.
Hi, I'm Sam Truex, and I've been working in the diagnostics and biotech industry my whole career, so I'm
Woohoo!
very excited to see this. This is really interesting. Can you tell us a little bit more about your vision for if you're able to validate that these breath prints are the appropriate diagnostic tool for humans?
Mm-hmm.
What's the practice of being able to do that in a place like Sub-Saharan Africa?
Yeah, so the question is basically how to translate what we're doing and what that might look like. And that's a very fair question. So we envision a number of different scenarios, and there may be phases within those scenarios. So in the West, we propose to basically transform the clinical microbiology space. So there would be a way to take breath samples from patients and then run them through a centralized system in order to monitor whether they're on a ventilator or a walking pneumonia type patient. At some point, that could be translated to a point-of-care device. And certainly in the developing world, that's where we're heading for a point-of-care device. So we focus on discovering the biomarkers, and we're agnostic to the way in which they are deployed. So I have collaborators that make miniature mass spectrometers, collaborators that make point-of-care doodads, to use a technical term. We don't care, but we know that they need what we have in order to really make a refined product. So I have some ideas on which things will work where, but obviously cheap and easy has got to be for most of these at some point. Yes?
So I would assume that people have a lot more individual variation in their genetics and in their diet than your mice did. To what extent do those kinds of variations affect your results? And if there's a lot of genetic variation, for example, would there be benefit of doing something like, as part of a routine physical baseline to something to get more of a differential of someone taking their diagnosis?
Yeah, that's a really great question. We try and think about both that bifurcation, both sets of directions from that bifurcation point. The personalized healthcare space where you monitor yourself and check in with that breath profile, if you will, over time. But then also looking for cross-cutting biomarkers. And as you indicate, there is genetic heterogeneity and susceptibility in the patient population in terms of their genes, also the bacterium. Let alone diet and other things. So that merely requires that you sample from many, many patients because that heterogeneity ultimately filters out. And we envision that there will be a cross-cutting set of conservative biomarkers, for example, for Staph aureus infection, but then there'll be subsets within and beyond that conservative set that may be particular to an ethnicity or a region of the world. Yeah, there's lots of variations on that, but there should be, based on what we've done and what we're doing clinically at the moment, a really conservative set that should work, but you have to validate. Lots of patients. Breath. All from over here. I'm expecting questions from over here at some point. One more there, and then we'll go here.
Hello, I'm Kathy Burke. Very nice talk. Thank you.
Thanks.
My question is kind of building on the previous one about the profile of the normal, so to speak, normal individual breath print. What's in the normal breath print?
Everything and its brother. Well, many things, depending on what you've eaten. So when we're taking a breath sample, you are trying to eliminate and suppress some of the things that are found in the oropharyngeal area. So we know how to at least suppress the oral microbiome, and that's simply done with a saline wash or a water wash. And we have them breathe deep breaths, depending on where we want to get the air from. Now forget your question. I got excited. Sorry.
What types of molecules?
That's right. I did say everything. It's breath.
Is it the disease and proteins?
No. So we're looking at small molecules, metabolites, typically less than 3,000 AMU. We're not looking at aerosols. That can be added on at some later point if you wanted to look for cytokines and things like that. But right now it's small metabolites, and they range from teeny little hydrocarbons to things that have been more oxidized at that smaller level through to longer branched things, ringed things, things with sulfur, depending on the bug. So a range. Yeah. And yes?
So this, drawing on Dave's question, a little further, going back to the medical, in chemistry, in chemical engineering section, obviously, breath print like diagnosis has broader application than just the lung infection.
Sure.
Because there are a number of other chronic conditions that are involved that have certain known breath markers and stuff.
Absolutely.
Diabetes and things like that.
Right.
So, is there a this kind of technology where you can have blood workups and breath workups and stuff in terms of looking at various conditions?
Gotta hope so. Absolutely. Yeah, absolutely. We actually do much more than lung infection work in my group, but that's primarily what we focus on at the moment. I do have someone in my group who is looking at Crohn's disease and monitoring flare-ups with Crohn's disease and other inflammatory diseases as well. But there's an enormous number of potential applications. So conceptually, it's very exciting, but developing that groundwork, as you know from Dr. Paulson's presentation, takes a good amount of time. So we focused in on an area where we know that we're getting some unique things from the organism itself, and we're not just depending on the body's varying itself, if you will. So we have that combination, which makes it a little bit of a lower hanging fruit than cancer or monitoring inflammatory diseases or whatnot. Any other questions? Thanks, Mark.